My talk is about some aspects of the research that is at this time in proof complexity, in particular about space complexity in algebraic proof system. This talk is based on this work by me and Nicola Galesi, in which we provide a framework for proving a space lower bound in this algebraic setting. And using this framework, we were able to provide an omega of n lower bound for random KCNFs that is an asymptotically optimal lower bound. So, starting from the basics, what is a proof system? It's a verifier that takes as input two strings, one that is a candidate of an unsatisfiable formula and one that is a candidate of a proof of this unsatisfiability, and checks in polynomial time with respect to the length of both strings if this is the case or not. So one very natural question is asking if there is some verifier or that is the same, some clever way of encoding proof of unsatisfiability that in such a way that the length of these proofs is polynomially related with the length of the original formula. And it turns out that this is the very same question of asking if QNP is equal or different from NP. So it's a huge open problem. So we have a lot of proof systems. One of the most well studied is resolution. For instance, we know that resolution is not an answer to the previous problem. And resolution, we can see working in this way. We have a CNF that is a bunch of clauses, and we can derive according to that rule some other clauses, and dynamically, I mean. And we have this property. If the empty clause is in this set we derived, then we can conclude that the original formula is unsatisfiable, and this property is an if and only if. Anyway, in this talk, we are not really interested into resolution, but we are interested into polynomials. So we have a ring of polynomial ring, an ideal into this polynomial, into this ring that is generated by some set of polynomials. And we want to, well, we ask ourselves if one is into this ideal or not. As before, we have this set of polynomials, and we can apply some rules that are written over there. And we can derive other polynomials, and we can check, I mean, we can move around into the ideal, looking for the polynomial identically 1. We have that this is a proof system because there is a way of translating CNFs into polynomials, and with the property that a formula is unsatisfiable if and only if one is into the ideal generated by this set of polynomials. Okay, in the next slide, I'll show you that we are interested into a space notion. This space notion is related with the number of monomials. So an encoding that causes a blow up of the number of monomials just for encoding one clause is not a really interesting encoding. So our results refers to a more powerful version of this polynomial calculus, that is PCR, in which basically we allow the same rule, but we use a more space-efficient encoding in which a single clause goes to one single monomial.
So could you explain what is this xi negated xi?
It's just we are enlarged the number of variables. It's just auxiliary variables to provide basically the semantic meaning of the xi negated is just 1 minus x.
So it's just a new variable.
Yeah, it's just to shorten the encoding. There is no big mystery around this. Okay, so the notion of space we use, so just recall somehow what a proof is. Suppose we have some sequence of memory configurations that is, we want to write actually our proofs somewhere on a memory of some computer in our mind on some blackboard. And so a memory configuration is a set of polynomials. And we move from one set of polynomials to another one, or by adding to the memory configuration some of the initial polynomial of the generator of the ideal, or we can apply some of the rule of the calculus, some of that rules. And so we can search if eventually we reach the polynomial 1. Anyway, we are interested into a more general notion of proof that is a semantical proof, in which that is more powerful, in the sense that from each memory configuration, we can move in one step everywhere we want, we can derive in one step every polynomial we want, apart that this polynomial is into the ideal generated by that memory configuration. So this is not a proof system, clearly, because we can add to the memory every initial polynomial. In one step, we derive one, so it's not a proof system. But if we obtain a space lower bound for this system, clearly it is a lower bound for a real proof system. Okay, so what is the notion of space? Okay, in the next slide I have a concrete example, so if it is not clear here, in the next slide it will be. So we have this sequence of memory configuration from one particular proof, and we look at some point there will be a memory configuration with the maximum number of distinct monomials in it. So this is the space we use to carry on that proof, and this is the space of that proof. And so the space to prove that one is into the ideal generated by that given set of polynomials is the minimum over all the possible proofs. So okay, let's see the example. We have this set of polynomials that is quite easy, and we ask ourselves if one is into the ideal generated or not. So at the beginning, the memory configuration is empty. We can add some initial polynomial to the memory configuration. We can add some other initial polynomial to the memory configuration. And then in one step, we can derive everything we want into the ideal generated by that two polynomials. We choose to derive this one. And well, you have to believe that it is into this idea. But, okay, so we can download some other things, and we can infer whatever we want. We can download some other things. We can download some other things, and eventually we have reached one. So we have shown that one is into this ideal using maximum space three monomials. At some point there were in the memory 3 monomials, and that was.
Can you just explain a simple thing? So when some polynomials disappear from memory configuration, so
yes.
So when?
Well, you
at any point.
Yeah, at any point.
So you can
Just
well, if you erase everything is useless, clearly. But the point is that you can save memory encoding just what you need to move on in the proof.
Like in the resolution proof.
Yeah, like semantical resolution proofs. It's close to that notion. Okay, so this is the notion of space. Let's see how it is briefly how it is related with some other notion that are in its neighborhood. So from the algebraic point of view, clearly an interesting notion is the degree of polynomials, clearly. And so I don't have put the notion of the degree in proofs, but I mean, it's quite easy. And in particular, it's interesting to see how this algebraic setting is related with a resolution for many reasons. In resolution, we have a lot of work, so somehow we understand quite well how resolution works, and we want to move this framework also in this algebraic setting that we don't really understand so well. And we have a lot of works about the degree, some Rasborov works, and so on. About space, we have only these two works that were previous to our work, and using our framework that I'm going to present in the next slide, there is also some these other works that is going to be presented in ICALP this year, and use our framework as a black box to provide a space lower bound for citing formulas, among other things. Okay, so one important problem that I want to focus is random KCNF. If the ratio closes over variables is above some threshold, with that probability they are unsatisfiable. So and it's believed that random KCNF are hard for every proof system. But in particular, for algebraic proof systems, it was not known if they were hard with respect to space. So to answer this question, we developed a framework, and then we were able to provide these proofs. So let's see from an high level of point of view how a space proof goes in our framework. I mean, this is kind of the statement of the main theorem, but it's not clear, obviously. So suppose we have this bunch of polynomial, and we want to prove a space lower bound. Suppose we have some combinatorial object that I call a good family of intalers of size k. Clearly, the red words are not well defined. But let's see how a proof should go. By contradiction, we suppose we have a proof of this combinatorial object that goes in small space. And we want to follow by induction the memory configuration, and for each memory configuration, we want to obtain some object from this combinatorial family of strange objects we have to provide. So one object that entails the memory configuration, that means satisfy the memory configuration, it's a set of zeros of that set of polynomials, or maybe maps that set of polynomials into some proper ideal, or something like this. But, and moreover, we have a notion of size that is bounded from above by some function of the actual number of monomials in that memory configuration. Suppose we have this, it's not easy to do clearly. Then we obtain that the last memory configuration, that is the polynomial 1, we cannot entail it. I mean, we cannot have some zeros of the polynomial 1. We cannot map the polynomial 1 into some proper ideal or something like this. But by induction, suppose we are able to prove that every memory configuration, we have some object from this family that entails it, so we obtain some object that entails the last memory configuration. And this is a contradiction. So where is the difficulty? To squeeze this notion of size when we squeeze the memory. That was also maybe your question. What happens when we squeeze the memory configuration? We have to squeeze also this object that we use to satisfy that memory configuration. So this framework works also in resolution. In resolution, it's easy. Okay. In resolution, it's easy because just for each memory configuration, we just need a single assignment. And the notion of size to an assignment satisfying that memory configuration in resolution. Here, no. Here, we need some more complicated object that I'm not going to talk to you about in details, but they are family of assignments with some combinatorial properties that we, with some difficulties, are able to maintain dynamically where the memory configuration change. And so these are the notion we use. It's a family of assignments with some independence property. I mean, we split this family of assignments into some blocks of independence, and this, the assignment in each block are combinable freely with the assignments in the other blocks. And this number of blocks is the notion of size. So it's not clear, but I mean, I don't want to be precise to don't put too much formulas in it. So, okay, the real statement of the main theorem is this. We have this bunch of polynomials, and we have some combinatorial property that is a k-extendable family of entailers that basically allows us to follow the proof, to maintain the induction property. So if we squeeze, we want to squeeze these entailers. If we download some new polynomials into the memory configuration, we want to enlarge these entailers to satisfy. So basically, to carry on the induction. So the advantages of this approach is that to provide a space lower bound, we don't need to deal with all the combinatorial stuff that are complicated to make this induction work. We just need to have this combinatorial object, a k-extendable family, that hopefully it's more easy to build. So for random KCNF, what can we do to provide a space lower bound? We build some omega of n omega of n extendable family. So to a random KCNF, okay, above the threshold where it is unsatisfiable, we associate a bipartite graph. On the left, we have the encoding of clauses as monomials. On the right, we have variables. We have edge. It's clear. And suppose k is greater or equal than 4, then we are able to provide by a standard union bound some expansion property on this graph that allows us to dynamically maintain some 2 matching in this graph. And from this, it's easy to build an omega of n extendable family. So we have built an omega of n extendable family, and for free, for the main theorem, we obtain a space lower bound. That is optimal because we can prove that every space a linear, we have a linear upper bound on the space, so it's optimal. So open problems. We have some big open problems that are how this space notion is related with other notion in this algebraic setting, how to extend these techniques to other proof system where a space notion makes sense, and we have a bunch of other open problems that are more, less high level. And one of them is how citing tautologies behave. So we have this result by Nordstrom, Filmus, and other people that proves some positive result on citing tautologies and other families, but it's not optimal. I mean, they prove some square root of n lower bound for some families of graph that use this formula, and so we have a gap, square root of n, and so we don't know. And basically, this is the state of the art of the space complexity in algebraic proof system. So, if there is any question.
So let me just start with a stupid question. So, I mean, is it true that any formula can be refuted with space, with linear space?
Yeah.
Is there an upper bound?
Yes, because we can do it in resolution, and we can simulate resolution in polynomial calculus. So, well.
So, any questions?
Is there any connection between the space and length, like in resolution? Maybe we have something with small space, then we convert it to something. Is there any kind of reductions?
About length, I don't know, but there is a result that is a trade-off between the space and the size, if I'm not wrong, that is by Beck and some other people. That is quite recent. It's last year. So.
A trade-off means that some of them should be big.
Yeah, one big, the other small, or vice versa.
My question was different. Imagine we know that there exists a reasonably short proof. Can we reduce it to a proof of very small size, or something have a short size, and we can get not very long?
Yeah, like
on the length of the proof, on the number of lines.
Or something. Just of course, I just completely.
No, I've not taken an example right now, but I don't believe that there is a connection so strong between these two complexity measures.
But I mean, why you believe so? If you need only a small, space, probably you don't need a long proof.
Well, but you can squeeze every time the memory, and you can. You can have a small memory, but you move a lot. You can change often what you have in memory. It's completely possible. You have some small memory, then you derive some other things into some ideal, and then you have some other small, and then you go on in this way, and it's a very long proof. But I don't have a combinatorial principle to.
So there is nothing like Benson-Wittgenstein reduction.
No. For this
It
case.
depends also. It seems that it depends on what you call the size in this case, because you have.
Yeah, clearly.
From the ideal just in one step. So
Yes. Yeah, actually, this is a real big problem because we are not really capturing the reasoning. In one step we can reach a contradiction without. It's not even easy to understand what is a proof in this setting because it's a semantical proof.
So, any other questions? If not, let's thank Ilario once again.